This is where you're doing three. You're integrating in z, y, and x, typically, or it could be other variables. We'll explore other variables later. So typically what you'll have is, like, if you're integrating in z first, then you're going to have the lower limit could be a function in x and y, and the upper limit could be a different function in x and y. And then y is next. That has to cut back down. When the second one here, you have to cut back down only in terms of this last variable. And then the last one has to be just the two numbers. And there are 6 different ways that this could, 6 different orders, because it doesn't have to be dz, dy, dx. It could be dy, dz, dx, or it could be dx, dy, dz. It just depends on the geometry and what in the situation that you're in, and how you can look and see the clear surfaces, okay, and being able to set it up, okay. And it requires a little bit more three-dimensional thought to do this, to set these integrals up. We'll get to that in a little bit, but first of all, let's go ahead and solve I'll solve an iterated integral. Okay, so the first one, you're going to integrate in y first, right? And so what did I say when there's no y's in here and you're integrating with respect to y or any variable?
This becomes 1.
Yeah, it's gonna, well, you're gonna end up with this.
Plugging the upper bound, yeah.
Upper minus the lower, right? Which is just gonna be the upper one. Okay, so that's gonna go from 0 to pi. That's the x going from 0 to pi, the z going from 0 to 2. And this y goes from 0 to the square root of 4 minus z squared. But since there's no y's in here, then what we're gonna get is we're gonna get the square root of 4 minus z squared, which I'm gonna write as this, because it's just easier for me to integrate this way. So I get to there. Okay. So now, next thing calls for integrating with respect to z. This is no different from the double integral, I think, at this point. And in fact, if we could have just started with this from the beginning, okay, and just had that, it would be a double integral. Okay, if it was like find the area between the surface and this region right here, blah blah blah, then it would just be this. Or yeah, okay. So anyways, we'll go ahead and integrate with respect to z, and that's going to give us 4 minus z squared to the 3/2. Dang, every single integral we've done has followed this pattern. Oh well. Except this one has a negative sign coming out because 2z, it's a negative 2z is the derivative, right? So it's negative 1/3. 4 minus z squared to the 3/2 sine x. And that is going from z equals 0 to z equals 2. Okay, this is interesting. When you put a 2 in for z, you get 0. Wow, that's nice. And when you put a 0 in, you get 4 to the 3/2, which is going to be 8. So that's 8/3. Okay, what's the integral here?
Cosine.
Yes, negative cosine is the integral because the derivative of cosine is negative sine. and you're going from 0 to pi. That's negative 8/3 cosine of pi plus 8/3 cosine of 0. This is -1 and this is 1. So you're actually going to get 8/3 plus 8/3, which is 16/3. Okay, so that's the first one, just kind of straightforward. Now let's get into something a little bit more difficult. So here we have an actual surface that's enclosed by E. E would be the like a three-dimensional region. So E is a three-dimensional region here. Okay, so we're enclosed by z equals x squared minus 1, and z equals 1 minus x squared, and then y equals 0 and y equals 4. Okay, so this is kind of weird looking. You'll notice that these two equations, which seem to be much more complicated than these two, but these two are only in z and x. They're only in z and x. So what I found good to do is graph them in the zx plane, okay, like that. So just think of this as being, you know, it's xy, but then just think of this as sort of like the xy plane, but it's x and z. That's the only difference. It's just the letter is different. Okay, so what is this graph going to be right here? Let's make that one green. This one here. Z equals x squared minus 1. Okay, yeah, that's a parabola. And where's the vertex?
-1.
Yes, the vertex is down here at -1, and it opens up, right?
Right.
So it's, what the heck was that? Dang, I wish I could draw better. Okay, and now this other one is, what is that? That's also a parabola. Where's the vertex?
+1 and it's facing down.
Yeah, and this one comes down. And these are gonna, okay, this is, come on, man. Okay, so these are gonna, they're gonna intersect here and here, right? Here and here. And what's that point right there?
+1 and -1.
Okay, good. +1 and -1. So x is +1 and -1. Okay. And so the region that we're looking at is this one right here. And so now we're ready to set up the integral. Okay, so we have the top one is z equals 1 minus x squared, right? And this bottom one is z equals x squared minus 1 is this bottom one. Okay, so if we integrate, so I'll give you a hint. So we got this x minus y there. We'll just put that there. That just comes from there. Okay, so I'll give you a hint. Let's go z first. And what do you think the limit should be on the z?
-1 to 1.
Is it x squared minus 1 to 1 minus x squared?
Yes.
Nice.
Yeah, so this first one typically has to be some kind of a function. Now, like on the first page, I said, typically it's going to be a function in the other two. So if this was doing z first, it would be in terms of x and y. Okay, but we are lucky that these equations that have nothing to do with y. There's no y's in those at all. Okay, so because what happens is when you do this, you need to, well, I guess another way to look at it would be to take a vertical line. And if that's x, then that's going from x squared minus 1 up to 1 minus x squared. Okay, or if it's over here, the same thing. It's going from x squared minus 1 to 1 minus x squared. So it's different. It's a different, for different horizontal, different vertical lines, you're going to go from different points. But it's always going to be from z equals this to z equals that. Okay, and then if we go with the next one, now this one, the dx, that one is going to go from -1 to 1. Okay, because this is -1 to 1 right there. Okay, and then what is y going to go from?
-1 to 1. Oh, 0 to 4.
Yeah, 0 to 4. Okay, so this is the y limits right there. So we have nice, these are planes actually. Y equals 0 and y equals 4 are planes. And so it's going from one bottom of the plane to a top. So really this region E consists of the inside of this going from 0 to 4. So if you look at it on its side, it would be kind of like, it would be like a cylinder, but kind of shaped weirdly with these sides instead of perfectly round sides. Okay, so let's go ahead and calculate that integral. Okay, so the z first, there's no z's in here, so it's actually going to be this minus this, which is 2 minus 2x squared. Oops. And so let's see, if we expand all this out, we have 2x minus 2x cubed minus 2y squared plus 2y x squared dx dy. Oh dang, I don't have enough space. Okay, so we can integrate that. That's going to be x squared minus x to the 4th over 2 minus 2x y. This is just a y here. This is 2y. So 2xy plus 2y x cubed over 3. And that goes from x equals -1 to x equals 1. Now, when you do this integral, when you put a 1 in here, you're going to get 1. And then you subtract and put a -1, you're going to get also, you're going to get 1 minus 1. So this is going to be 0. And this is going to be 0. That's when you plug the upper and lower limits and subtract. Because the upper and lower limits give you the same number, but you're subtracting them. Okay, this one right here, you put the upper limit in, that's going to be 1. That's -2y. Subtract the lower limit will be another -2y. So that's minus -4y. And this also is just kind of double up. So that's going to be, there's a 1 in here plus another 1. So that's going to be 4y over 3. Okay, so you can get a common denominator here. So this is the same as negative 12y over 3. And so those add up to negative 8y over 3. And the integral's negative 4y squared over 3. That's going from 0 to 4. That's negative, put a 4 in there, that's 16 times 4, that's 64 over 3. Okay, so that should be the answer, hopefully. Okay, so negative 64 over 3. Any questions about that one? This is just giving you kind of an introduction to triple integrals. Okay, so let's go on to number 3.
Brother Hurst, did they ever have quadruple integrals?
Yeah, you could, but they're kind of, it's going to be hard to visualize. So we don't, I've never done any.
Okay,
So
cool.
I guess you could write one down. You could write as many as you want and solve it, but who knows what it would mean, you know? Who knows what the physical significance would be? Okay, so use a triple integral to find the volume of a solid enclosed by the paraboloid. So this is y equals x squared plus z squared, and y equals 32 minus x squared minus z squared. Okay, now generally, the standard way of doing things is to have the z-axis pointing up here, right? And then have the y there and the x coming out this way. But this is in terms of y equals something and y equals something else. So we could stick the y coming up like that, which means that the x would be, I guess the x should be right there, and this would be the z. You can do it that way. And then, because what happens is, here you have this surface right here, y equals x squared plus z squared. So that's actually, that's coming up right, that's coming up this way, right? That's some surface coming up, that's some surface coming up this way. Dang, this is like really bad. Coming up that way. And then you have this other surface here, this 32 minus that. And that's like, if this is 32 right there, then this one's going to be coming down this way. Okay. And so it's kind of like a distorted sphere-shaped object, like one paraboloid on top of another. So the E, or the solid, is going to be what's inside both of these. And the first thing is to say, okay, where do these two intersect each other? That would be the first objective. And so how could we find out where these intersect each other?
By making them equal to each other.
Exactly. So we set them equal to each other. So we know that we have y equals something here, we have y equals something there, so we just set the other part equal to each other. And bring these over here, you get 2x squared plus 2z squared equals 32. Divide everything by 2, you got that. X squared plus z squared equals 16. So that is a circle of radius 4, right? Circle of radius 4. And so what you need to do then is come down here to the, is project the circle down into the XY plane. And that's what we're gonna, that's gonna be what you're gonna grade in second. Okay, so first, so what you're gonna integrate first is gonna be from x squared plus z squared up to 32 minus x squared minus z squared. Okay, dv. So to find the volume, just integrate just the volume, the dv. Okay, and then here, this is a circle, right, or a disk. This disk right here with center 0, 0, and radius 4. Okay, so what I'm going to do is I'm going to do polar coordinates on x and z. You can do that. So x equals r cosine theta, and then I'm going to have z be r sine theta. Okay, and everything else work out. So that now this goes from, so this becomes r squared, right? And this becomes 32 minus r squared. And then the dv is going to be, well, you're going to have the d, you're going to have dy first, okay, and then you're going to have r dr d theta. Okay, so you can do polar coordinates on x and z as opposed, it doesn't have to be y and z. So you can, like, depending on the situation. Okay, and then the r is going to go from where to where? So this part of the integral, these two right here, is just this blue disk right here in the xz plane, which that. So r goes from, the radius goes from 0 up to where?
4.
Yes, that's going to go to 4. And then theta? From 0 to 2 pi, because you're going all the way around. Okay, so great, that's the integral. And let's go ahead and solve that. First of all, there's no thetas anywhere here, no theta there, that's not a theta, that's not a theta, that's not a theta, that's not a theta, no thetas anywhere. And it's the last one. Okay, so there's no thetas anywhere, that means we can just put it, we're going to put 2 pi minus 0 on the front and dispose of this last one here. Okay, then dy is the first one. There's no y's anywhere. So you can just take that minus that. That's 32 minus r squared minus r squared. That's going to be 32 minus 2 r squared. That's all going to be multiplied by r, though. Dr. That's it. Interesting. Okay, so 32r minus 2r cubed dr. So now we integrate. This is going to be 16r squared. And this one is going to be r to the 4th over 2, right? And you're evaluating it from r equals 0 to r equals 4. So let's put a 2 pi in. Okay, so you put a 4 in there, and that's going to be 16 times 16 minus, and this is r to the 4th, that's 4 to the 4th. I'm getting 256 pi.
That works.
Okay, so 256 pi, and okay, well, this is awkward because we finished up all the homework. Well, that's weird. We finished 2 sections of homework.
How many more sub-chapters for this, for chapter 15?
3 more.
3 more? Is it next week exam?
Yes, it's going to be on Thursday.
Thursday?
Yeah, so exam 3 is going to be Thursday. So that's interesting. The next section is triple integrals and cylindrical coordinates. And this problem that we just did, this number 3, is actually cylindrical coordinates. Okay, we basically just use cylindrical coordinates, which is like polar coordinates, except you have another variable here, except this is 3 variables. So the third variable, just leave it alone. So this dy stayed, we left it alone. But we took the x and the z and we changed them to we did polar on that. So that's basically what cylindrical coordinates is. And then section 15.8 is spherical coordinates. And I'll explain those later, I guess, when we get to it. And then 15.9 is just change of variables in general. So the idea is that we went from, so the idea is that in triple integrals, you have, the main ones is just rectangular coordinates, cylindrical coordinates, and spherical coordinates, but there can be other ways you can do it. And section 15.9 kind of explores what you need to do for that. Okay, so, and part of it is, like, for example, when we do polar coordinates, we get this r coming in here, right? The same thing with cylindrical coordinates. So the dv is, this dv right here becomes all of that, becomes all of this. Okay, instead of just, so in rectangular, it's dy dz dx, or dx dy dz, or something like that. But just those, just the dx dy dz in some combination, in some order.